I'll just quickly see my bios up there. I'll introduce myself. I'm Graham Kneller from 3D Technologies. You may know the ProSec brand as well, but this is a Swiss company that produces non-destructive technologies. And excuse me, we work purely as a manufacturer and developer of software. And the service element is provided by experts like Warren Thomas and his company, Henderson Thomas. So I'll hand over to you, Warren.
Click on. I don't know what's coming up next because that's me. On we go.
That's glasses. And there's the geospatial QR code. If you've not had it already, please. If we've got time, we'll answer questions at the end of the session.
What we're trying to do is, because this is one that normally takes 45 minutes, we've had to just put it down to 20. I will try and go through it quickly. We do cover a lot, so by all means do actually put the questions on there, and if we have got some time at the end, we'll go through to it.
So we're basically going to go through and other forms of NDT technology using in different applications and different types of structures as well.
What you tend to find is the issue that we have is, and it's very much what Commit is trying to get across, the amount of times people go, well, we've always done it like that. And I go, yeah, and that's why bridges keep falling down and buildings keep falling down. So what we're trying to do is to bring some innovation into our market, and as a lot of you will know, it's like trying to push water uphill. So we're talking about a couple of types of NDT, predominantly ground penetrating radar, and another technology called, generally known as tomography, but it's ultrasonic. So they're two quite different techniques, hopefully to give us a far better idea of what's going on in structures.
You can more than welcome to come and look at the units as well and show you what type of data you get from them.
So this next slide, talking about radar first, it's been around for donkey's years. Really, the growth of it was in the 70s, and this was the sort of equipment we had. And if you can think, being in the middle of a field with one of these printers with a radar transducer, and you had to normally run it off of a car battery. So it was really sort of like Heath Robinson. But since sort of mid-70s into the 80s, it's really been pushed forward for the application. So now we can use it for, it was predominantly used for detecting services, so gas pipes, electrical pipes and such like. But now what they've done is with these smaller handheld units, it's far more reaching, as you can see. One of the things I'd say with any technology, and again, it's the real thing about what Commit are talking about, it's really important you know what technology is out there. So people can say, oh, ground penetrating radar, tomography. Far more important than that is how we can apply that technology to applications, because you, as maybe the end user or an asset owner, is going, well, that's really good, GPR, but what does it do? What can it tell me? So here are a few things that it does do. And one of the things that I will do talk about is we do want to know what the limitations of the techniques are, because I would like to undersell, over-deliver rather than the other way around. And radar is one where anybody can pick it up and get some sort of information, but it's how much that information actually is going to be important to the client. So this is going to be something where this is a live scan that we've done this is on a rail bridge over the M25. So this is, I don't know if anyone has any idea what we're looking at here. So what happens with radar, it sends a high energy wave into the concrete in this instance, and I used to say it was materials of different densities, and then got my wrist slapped by a GPR engineer. What we're getting here is we have, and you'll see on the test block out the front, when you have rebar in a slab, the rebar will have what they call dielectric constant. And the concrete will have a dielectric constant. So the dielectric constant of the concrete is around about anywhere between 6 and 10. Rebar is infinity. Water has another dielectric constant, as does air. So where you get materials that have got quite distinctly variant dielectric constants, you can pick them up really well. So what we're getting here is, these are rebar. So as the scan comes in, it starts to pick the rebar up, so it's quite a weak signal, gets stronger, and then drops down. And what you can actually see here are details, or they're called post-tensioned ducts. So this is post-tension concrete. You will have heard of a bridge that fell down that was post-tension. That was the Genoa Bridge in Italy. What you have here is these. You can see these. The targets are far bigger, and that actually indicates that we're looking at a far bigger area. That sort of size against rebar that was probably 25 mil diameter. And what's really important for us is when we're looking at post-tension structures, this is the A40 elevated. So what you've got here is you've got a big void in the deck. This is your concrete slab and cantilever. And at this section here, these little round dots, they're the post-tension cables. That effectively is what's holding this bridge up. Similar to the design at the Hammersmith flyover. Anybody drives underneath the Hammersmith flyover, you'll see what looks like big drain pipes. That is now externally post-tensioned because these were in such bad and poor condition. They're defunct, so they're not doing anything. So they've had to bolt on extra supports along this side of the bridge that you can see. So that's what we're looking at. It can get to the point where the bridge could fall down, and we've had a number of failures across the world. And what you can see here is, this is actually a radar scan using the ProSec radar here that you can see up on the right-hand side. So what you can clearly see is this is what we call the back wall echo. So this is imitating this cantilever section you can see here. This is the top of the deck, which you can see here, and you can quite clearly see targets. Now, because you've got two lines of targets, even radar has an issue with picking something up that's directly behind something else. But you can clearly see these are the targets that we then have to investigate to determine the condition. As I said, what you've got here is you've got a sheath that has metal wires running through it. The problem that we have is, and why it's a hidden defect, is these can corrode merrily, and because they're in a sheath, we get no outward sign, no cracking, no rust staining that you would normally find in other concrete, in other standard concrete. So that's why we needed to locate them quickly. Previously, you just go along there with drawings and have to stitch drill until you found them. So if you're looking at bridges, well, for instance, we do a lot of work for Network Rail. They have a number of post-tension bridges. We've got anywhere between 2 and 4 hours on a shift to do the investigations. So if you're spending half your time trying to find the duct to then actually open it up and work out what's going on. So this is where technology is clearly saving us a lot of time. Do you want to go?
So I was just going to say this, what you're seeing here as well is just by doing one scan, you can actually flick through different views of that. So you're not having to sort of do this hyperbola type scan here and then do that one separately. You just do it once and then you can swipe through different views to be able to attain what it is you're trying to justify.
What we found with a lot of engineers, we would show this and they'd go, no, don't get it. I think, no, but these are bars. No, don't get it at all. What's this scan called? I can never remember the
A-scan.
With the A-scan, it effectively produces like a nice little round circle, and you're going, no, these are the rebars, and they go, oh, I can see what you're getting on about now. So having different scans, the A and B scan, gives us a far, hopefully, easier way to explain to the client.
And again, just by doing one scan on site, you can actually create this into augmented reality at the time. So if you're actually trying to run through the client engineer and explain the situation, you can the movement we've made from hyperbolas and line scans to this type of technology helps you move very quickly in being able to make decisions. And if you're actually applying, for example, remedial work and coring, you can just mark that out on the wall as you see it there and then. So these are all very much quick and easy advancements that are instantaneous to undertake that help the industry move on a lot quicker now.
Yeah, so this was to do with a cross-rail project where they knew they had some structure underneath the road. They didn't know which way it was running, and so what we've got here is we've got a jack arch, and this jack arch is supported here and here by a couple of massive, great big sort of cast iron beams. This actually was running in completely the opposite direction what the guys at Crossrail thought it was. So they were very pleased about that, because they were going to have to base their works around this. And so this is what we found. What we did is we drilled a hole through from the road above to actually put a boroscope in to actually get some definitive information. With all of the NDT that we're looking at, you do have to do, have to do some calibration, because a lot of the kit will tell us something, but it may not tell us exactly what's going on. Like some of the kit out there we've got will tell there's a reduction in ultrasonic pulse velocity, which means the concrete's not as good as it should be, but I can't tell you what it is. Is it compaction? Is it corrosion? Is it things like fire damage, frost damage concrete? All of these can reduce the ultrasonic pulse velocity, but I can't tell you what. So that's where we take cores and examine it. So there does need to be a gentle hand guiding someone going, you do need to calibrate this, guys, as well. So here, the problem with this is everyone goes, oh no, these are the arches. No, these are the big steel sections that we're getting a really good reflection on. And what you're getting actually, these are the arches here that you can just about see. So again, it's ensuring that you know what's what. And unfortunately, a lot of firms who do radar think it's always a black box. We have to tell everybody, you need to be a brain surgeon to work it out. No, let's make this as idiot-proof as possible and ensure that the client can see what we're doing and what information we're getting from it.
So this just shows
Couple of
examples,
So what we've got here is this was a pre-stressed post-tension beam in Scotland. They knew they had issues with the grouting of the duct. Normally it's filled with cement to protect the metal rope inside, which is tensioned up. However, this one they knew there were issues. So what we had to do was use tomography, which we'll come on to next, to work out what's going in the duct. But for us to do that, because the ducts don't run straight, they run there's a profile to do with the load-bearing capacity of the bridge or beam in this instance, so you need to know accurately. So this is where we used the radar to, this is, as you can see, it's coming down. As it gets to mid-span, the ducts will be low, and when they're at the end they'll be high, again because of the load-bearing capacity.
Just move on, and this is one of Warren's favourite.
People ask, what are the applications? Now that is a barrel of whiskey, and what we're looking to find there is, the boring explanation is, when whiskey is put into a barrel, it's left there for, if anybody drinks whiskey, you'll know I'm preaching to the converted, it's normally kept in the barrel for 12 years at least, or 24 years, 25 years, or 40 years in some instances. And it's not taxed. So when that gets taken out of the barrel, it's then taxed. So what this was Chivas Regal, and what they wanted to know is how much had evaporated. And in some instances, the barrel can be half empty. And the Scots, being a canny race, would say, oh, it's always a lot more empty than it actually is, because they wouldn't be paying tax on the whiskey. And they call it the angel's share. And it's there, the thing up there is, it's the angel's come in and taking its wee nip of whiskey away. Now, people say, what can you use radar for? You can use radar as a glorified cover meter to work out where rebar is, or post-tension ducts, or you can determine the angel's share. And there's a lot between the two. So it's just giving you an idea of, you can really apply it to a lot of things. When we move on to the second phase, and a lot of this work was to do with post-tension structures where we had major issues. A bridge fell down in South Wales in 1980, and everything's hidden. So the big problem was to try and work out what is going on in these ducts, which are hidden in the concrete. So with radar, at least we can detect them, but with tomography, what we've got here, this radar, when it hits the sheath, the entire signal is reflected back, so nothing's going to go through metal or steel with radar. It's just the way it works. However, with tomography, about 50% of the signal will be attenuated, meaning the rest of it will go through, and when that's reflected in air, we get a really good response back. So what I've been looking at is, so this is a duct, and this is the back wall of a web, pretty similar to what we saw earlier. So what you can see here is you can see distinct targets. Red blobs equals an air gap, which we don't want in these tendons, because the risk for us is if there's an air gap and water gets into it, and we pour hundreds of thousands of tons of salt on our roads in the UK every year, and if you're in a marine environment like Genoa Bridge, and that marine salt or de-icing salts can get into the tendons, it can cause corrosion. Now, if it's fully encapsulated in grout, as they should be safe. So we're looking at, if you can pick up the air gaps, you can pick up the high risk. So this is the same beam we were looking at earlier. So you can see the tendon locations marked on, and this is the pundit, which is sending ultrasonic pulses in. And each one of these is a scan. So we've got a lot. And you can see the profile of the tendon going down.
This is an example here. Warren, you'll talk through this about how you can actually find under object at spot A is what we don't want to see, and actually spot B is a little bit more reassuring.
So what you've got here is, this is the expanded aluminium sheath of the tendon. These are the metal rope that's actually in there. So this is the post-tensioning strands. And what you should find is you should hopefully have this nice grey, battleship grey grout. Now that's what we want to see. We want to see it fully grouted. So that means the wires in there are fully encapsulated in it. And I won't go on to it, but that produces an environment where the bar won't corrode. Here though, because we've got the gap, it's going to allow potentially to corrode if you're getting moisture coming in. And again, you can see these were the scans we got here and the scans on the other area. So this was the first time it had ever been used in action in the UK. I think it was about 2017.
I was at a meeting recently in National Highways, and they quoted that without using this technology, only 10% of the time were they able to find where there were voids, whereas by using this, they're now over 80% they're getting the correct void locations. And so that saves them so much time and money as well, which is good for us as taxpayers.
And again, working on the A40, you can see the tendon profile here, and we were doing a lot of work, and this is what you don't want to see. Just flick it on quite quickly now, because we all know we got.
So again, this is just a quick example of what you're able to ascertain, again, while you're on site. You'll see the slider going down, so that's going through different depths, and each time it's picking up a void in another location. And then if you swipe that into the 3D, that's giving you, in real time, an image that you can really then interpret as to what you're actually finding beneath the surface on there. Again, this is just another example of projects where it was used to ascertain a void behind the actual wall that was in there. And as you can see, when you've actually drilled into it, there it's really showing through there in visual terms.
This was a shotcrete repair on a badly chloride-contaminated piece of concrete, and the client had done some work, used the wrong technology, didn't bring anything, and he said, I don't think we've got any voids. I think you have probably got voids, you haven't used the right bit of kit. And well away from an area that had a problem, we found this. So we're going, this doesn't look good, guys. This should be fully grouted. You shouldn't have like a little, dare I say, Tolkien-type cave in there.
Yeah, but again, those tools that Warren uses shows you don't necessarily just rely on one thing. You even go back to boroscope to get that visual image. You piece it all together because it comes back to that data aspect and being empowered by data. So again, this just shows a quick video of what potentially you'll find when you get the points.
This is a tide coming under a large piece of concrete. There was a ramp going down. The water was coming up. Obviously, it wasn't being supported underneath. We've had failures of dams because of being washed away. So it's really important that people know what's going on. Just whiz through. Yeah.
Basically, using the GPR, it wasn't actually determining what they wanted to find because they knew there was an issue, but they couldn't understand it. So using the ultrasound, which has a lot more uses to it, particularly finding voids.
This was a massive slab in a warehouse where just keep going on, get through to the photographs, show it all. And what happened was they used radar, it didn't work because it was a metal fibre reinforced slab, so all the metal fibres, just looking like the size of matches, about that long, just reflected all the radar signal away, no area. And what happened, I'll show you why we were called in to do this, but very briefly, these are the three types of plots we had coming out. Good, small voids, really bad. Again, you can probably click on from this. This is what we had. This was the good concrete. That's what we had. They cut some sections out, fully compacted, lovely. We had this one which showed these targets, which showed little voids, and when they cut a section out, this is what we were getting. So here are the metal fibres. There is some reinforcement in there as well. Not ideal, but we couldn't work out what was going on here initially, and we had a chat with the guys at Screen and Eagle because signals were coming in and they normally get reflected back and get picked up by the kit. But because the void was so big, as the signal came down, it came off over here and wasn't picked up, but it was indicating that's not what you want in your slab, is it? Especially if you're drilling in, trying to put anchors in to have a really high racking system. And this slab was 6,500, 7,000 square metres, and we had to test virtually every square inch of it.
It's just the piece upon piece was cut away by the plant, and so the point we wanted to make was actually just to, I won't go through the videos, is because it make sure all of these different types of collected all together, and ideally it would go into the GIS that we were talking about in the previous presentation. But it's vital to use those different tools that are there to be able to enable the right decisions to be made. And this happens time and time again on existing infrastructure, but on new projects as well. We see it up and down. Every major project that we have in the UK at the moment will need this technology because there's a quality issue. Okay.
Sorry, there's a fair bit to run through. If you want to, we'll be out all day tomorrow as well. By all means, come up and have a chat. And if you want to, you can pick up some of the kit and roll it over or throw it at the concrete slab we've got there, and we can show you, what it does.
Yeah, okay. Thank you.
Thank you.